A very good morning to everyone. I welcome you to the second day of 1 week national workshop on advanced synthesis and characterization techniques organized by Department of Applied Physics, Amity School of Engineering and Technology, Amity University. Today we have with us eminent speaker Dr. Anupama Chanda. Dr. Anupama is Assistant Professor, Department of Physics, Dr. Hari Singh Gaur, Central University, Sagar, Madhya Pradesh. She has done a PhD in Material Sciences from IIT Kharagpur in 2009. She was a postdoctoral fellow at Chungnam National University, South Korea from August 2009 to August 2010. Then at Korea Advanced Institute of Science and Technology, South Korea from August 2010 to August 2011. And then she was again a postdoc fellow at Institute of Physics, Bhubaneswar from November 2011 to June 2013. She has, to her credit, academic awards of being qualified GATE exam, then CSIR NET and JRF, and CSIR SRF. She has more than 30 papers in national and international journals, and she has more than 20 papers in national and international conferences. Her areas of interest include growth and characterization of semiconductor thin films and nanomaterials, study of dilute magnetic semiconductors for spintronics applications, graphene and graphene-based hybrid systems, study of conducting polymer and their composites. May I now request Dr. Anupama ma'am to kindly address the guest.
Okay, thank you, Dr. Madhavi, for giving such a nice introduction. First of all, I would like to thank the organizing committee and the team members for organizing such a wonderful and useful workshop on advanced synthesis and characterization techniques, which will be of much help to the students and also as well as faculties in their research career. And I would also like to thank Dr. Manisha Singh for inviting me to give a talk on this thin film synthesis technique. Thank you all. So now, should I start?
Yes, ma'am, please.
Yes, ma'am.
Okay, so my talk is on thin film synthesis technique. So nowadays, first of all, I would like to say that this is the thin film technology, that is advanced technology, and which is used in all the aspects of our day-to-day life. And the material applications in this is applicable to the various fields like optoelectronics, electronics, biomedical, intercalation, that is your batteries, thin film transistor, photovoltaics, all these materials can be in thin film forms. So now question is, all these materials will be in thin film form, and that is, the question is what this thin film means. That is the thin films. Here you can see one example of this thin film system. In this case, we will see that is solar panel here. That solar panel, this is very good example of a thin film. So here we will see that is the solar panel. This solar panel consists of this solar cell, and this solar cell consists of several thin film layers. And this solar cell, that is in thin film form, that is cadmium selenide telluride and cadmium telluride absorber, that is used to harvest maximum solar irradiance and to convert the maximum power to electrical energy. And the maximum efficiency obtained in this thin film solar cell is 22.1%, which is much better than the amorphous silicon. The silicon solar cell we are using, that silicon solar cell, that is far better than this silicon solar cell. This compared to silicon solar cell, this thin film solar cell is far better than this amorphous silicon. So, and this cadmium zinc telluride is also used as an interface layer, that is also in thin film form. So now, question is, what is this thin film? Thin film, as we know that, it is a thin layer of material where the thickness is varied from several nanometers to few microns. And the structure of this thin film can be, pardon, sorry, are you able to hear me?
Yes,
Am I
ma'am.
audible?
Yes,
Yes,
ma'am.
ma'am. Yes,
Yes,
ma'am.
ma'am.
Okay. So the structure of this thin film is divided into, it can either be amorphous structure or it can either be polycrystalline structure, depending on the preparation condition as well as the material nature. And this thin film generally comprises of two parts. First, the layer and the substrate where the films are deposited on it. Here you can see the substrate, and on this the thin film. Substrate is a primary requirement for thin film deposition. Otherwise, we cannot. Where we will deposit this thin film? So now the question is, we are talking about thin film. So what is this thin film? Means how much thick it is. Film, it is one kind of a material that is coating, that is deposited on substrate. So how much thick it should be, so that we will say it as a thin film. So how much thick? Now here we can see this diagram, that is thick film, that comes under, this is the thickness of this thick film, that is around from 1 micron to 100 micron. If the thickness of the film material is from 1 micron to 100 micron, then we will say it as thick film. But if the thickness lies below 10 angstrom and up to 1 micron, then we will say it, or we will categorize it as thin film. And what are the advantages of this thin film, or why we require this thin film? That is, this thin film generally are used to modify the surface properties of engineering components by applying thin metal coatings. And these modifications are diverse. That is, able to affect the material properties like conductivity, wear, fatigue, corrosion, hardness, and much more. Depending on our requirement, we can use the thin film for various purposes. And the common thin film applications you can see here: optics, electricity, computer, magnetics, thin films, that is CD, DVD, and solar cell. All these are various applications of thin films, and we will come to this also later on. And the main advantages of this thin film technology, that is the most important, is tuning the material surface properties. That is reflection, absorption, hardness, abrasion resistance, corrosion, and electrical behavior. And the most important is cost reduction and miniaturization of the device. Because of reduction in size, there is miniaturization of the device. That can also be sometimes also it is for flexible application, that can be flexible, transportable. So for this purpose, we generally we use thin films. Now, this deposition of thin films means what is the mechanism here? That is how the way thin films forms. Different stages or different phases. That is, first it goes to, that is your adsorption, then diffusion, then nucleation. That is, adsorption means, suppose there is some material is there, that is in vapor form or liquid form or any other form, gas form. So first adsorption means, that is first add atom or atom will be adsorbed on the surface. Then there will be diffusion of the add atoms. Add atom means that is the atom which is adsorbed on the surface. Then there will be diffusion between the add atoms. Add atoms will diffuse through the surface. Then nucleation will take place. That means that add atoms will interact with each other, forming the crystal. Nucleation is the first initial phase. It is the initial phase to form any crystal from vapor, solution, or any gas atoms. That is the initial stage, initial phase that form the crystal. That itself represents the whole crystalline structure. That is the nucleation. And this nucleation, surface diffusion, adsorption all depend on the material and the substrate properties and deposition method and parameters. The interaction between adsorbents and the substrate. Again, adsorbent means that is the substance which is adsorbed, and the interaction between adsorbents and the substrate surface determines the growth mode and the structure of the resulting thin film. And these are the different stages. That is, during the growth of thin films, different mechanisms occur at different stages. These stages are surface preparation, add atoms and surface diffusion, nucleation of add atoms, island growth. That is surface preparation. First, surface will be prepared. That means your substrate surface will be prepared for add atoms to come and sit there or getting adsorbed there. Then add atoms will come and there will be diffusion of add atoms. Then after that, nucleation of add atoms will take place. After that, there will be some cluster formation. Then those clusters will form island growth, or then they coalesce and form continuous film growth. This is again the steps. This is the schematic representation of a processes leading to nucleation and 3D and 2D film growth. Here you can see the schematic representation. What I told, that is, first we have the either vapor or some atoms are there. Those atoms will come to the substrate surface. There will be thermal accommodation. Means this substrate surface and the atom, there will be thermal accommodation, means that substrate surface may be at some temperature and the atoms will come. That can also be at some temperature. So there will be thermal accommodation of the atoms on the surface. Then these atoms will diffuse on the surface. Then either that will be absorbed on the surface or it will again re-evaporate. And in the meantime, some metastable cluster will form. Then when that cluster size will reach a critical cluster size, then we will say some stable cluster will form. After that, there will be island growth, depending on the cluster, 3D-dimensional island growth and 2-dimensional layer by layer growth. This is given here. Whatever I told, this is written here. And at sufficiently low temperature, a fraction of the clusters which are formed continue to grow in size and become islands, which eventually impinge and coalesce with their neighbors to form. That means cluster will form first, then they will coalesce with each other to form a continuous film. Either they will form continuous film or they will form island. That will depend on some condition that we will see again. And in this case, at high deposition rate, if deposition rate is high, or if the substrates, that is the low temperature, deposition temperature, then what happens? The film is amorphous. This occurs since the add atoms do not have sufficient time to diffuse to low energy sites before they are buried by subsequently deposited add atoms. That we know very well. That is, whether that film, whether that is amorphous or crystalline, that depends on some factors. That is, one is your deposition rate, that is substrate temperature. So depending on that, how much time it takes to nucleate on the surface, then depending on that, it will be amorphous. Amorphous when it will be when much greater than NS/DS. Here NS is the substrate surface site number density and DS is the add atom surface diffusivity. If R is much greater than, generally some techniques are used, or some techniques, in some techniques we get amorphous films and some techniques are used to get crystalline, highly crystalline films also. So those we will discuss here. Here some growth modes. Growth modes means after the cluster forms, then we will see whether that clusters will coalesce to form, that is layer by layer growth or island growth. Here, there are 3 different growth modes. One is Frank van der Merwe growth, that is layer by layer growth. In this growth mode, the adsorbate surface and adsorbate. As I told, the adsorbate means that is the adsorbed on the surface. So adsorbate and surface. And adsorbate interactions are balanced here. In this case, that is layer by layer growth occurs when the adsorbate surface and adsorbate interactions are balanced. And Stransky-Krastanov growth. In this case, you can see that is here it is the layer by layer growth and also island growth is there. So in this growth mode, the adsorbate surface interactions are stronger than adsorbate interactions. And Volmer-Weber mode, in this growth mode, the adsorbate interactions are stronger than adsorbate surface interactions. Hence, islands are formed right away. These are some conditions. whether when the layer by layer growth will occur or island growth will occur. This is also mathematical requirement, how the mathematically we will discuss. We can see that whether island growth will take place or layer by layer growth will take place. Here you can see the schematic of a film island on a substrate. That is here, gamma S is the surface tension of the substrate surface, and gamma F the surface tension of the film surface, and gamma Fs that is the surface tension of the film substrate interface. And the balance of forces acting along the substrate surface yields, that is gamma S is equal to gamma S by F plus gamma F cos phi. For the case of layer by layer growth, phi equal to 0. The angle between your gamma F and the gamma S by F or gamma F by S. Here phi equal to 0. When phi equal to 0, then layer by layer growth. This is just, we can, evidently you can say that it is okay. When phi equal to 0, then there will be layer by layer growth. And from equation 1, we have the condition for layer by layer growth. That is gamma S is greater than or equal to gamma S by F plus gamma F. Here layer by layer growth occurs. And for island growth, that is Balmer-Weber mode growth, that is when phi is greater than 0. And corresponding condition is, that is gamma S is less than or equal to gamma S by F plus gamma F. Here island growth occurs. And for layer plus island growth, the condition 2 first will be satisfied, and then intermediate layers alters the value of gamma S and gamma S by F, leading to the condition 3 for subsequent island growth. These are the mathematical discussion. And earlier, how we saw how surface preparation, then odd atom formation, then diffusion, then cluster formation. Those things are theoretical, and this is your mathematical. Here it is the total things what occurs during the growth. Here we can see that is first is nucleation. Nucleation is the initial process of crystal formation. That is here first thermal accommodation will take place.
नहीं रुका है वो कुछ नहीं इंटरव्यू हुआ नहीं.
Thermal accommodation will take place. There will be diffusion of odd atoms. Either they will be adsorbed on the surface or dissolved. If it is adsorbed, then they will interact with each other, forming the cluster. Then when it reaches a critical cluster size, then stable cluster will form. After that, we will get whether it will be island growth or layer by layer growth or Stransky Krasnov growth. Now, thin film deposition methods. So now we will discuss about various, that is the main motto here, that is the thin film synthesis techniques. That is, we use two different techniques for thin film deposition. One is your physical deposition, another one is chemical deposition. And in physical deposition, we have different techniques like evaporation techniques, under which vacuum thermal evaporation, electron beam evaporation, laser beam evaporation, arc evaporation, molecular beam epitaxy, ion plating evaporation occurs. Also, sputtering techniques also comes under this physical deposition. And in chemical deposition, we have sol gel technique, chemical bath deposition, spray pyrolysis technique, plating, electroplating, electrolysis deposition, chemical vapor deposition, and under this chemical vapor deposition, LPCVD and PCVD also comes, then atomic layer deposition. So physical vapor deposition generally that utilizes a physical process to deposit thin films. And here physical process means, that means here the material which is deposited, that is the material here, this is the substrate, and here we can see that is the material here, that is the target material, that is first vaporized from a solid form into plasma or ions. In physical vapor deposition generally, that is, it is from a solid form that will be vaporized to ions or plasma. The target material is then transferred to the substrate surface and allowed to condense and grow into a film. Here you can see that is the evaporator here, source material here is placed, heater is there, that can be resistive heater, or that can also be E-beam evaporation, that we will see later, the next slide. So here it is resistive heating. So evaporator is here source material from source material, that is when it is heated goes beyond its melting temperature, it is vaporized and forming ions or atoms. These ions are plasma, and these ions are getting deposited here on the substrate, and that will form a film. Here, vacuum thermal evaporation, that is in evaporation technique, we have first two nice deposition technique. That is, one is your thermal evaporation technique, another one is E-beam evaporation. So in thermal evaporation, that works by vaporizing the target material using thermal energy from a tungsten heating filament. Tungsten heating element. So here, after vaporization, the material is transported through a high pressure vacuum and is deposited onto the substrate where it condenses and grows into a solid film. This method can be used to deposit pure metals, non-metals, oxides, and nitrates. It is most often used to deposit electrically conductive metallic layers on solar cells, OLED displays, and thin film transistors. Here, the main advantages of this thermal evaporation, that is, films have higher purity and good quality. You can see that is impurity incorporation due to high vacuum condition and widely used to form. It is generally used to form metal contacts to the devices. That is most important advantage, that is used for metal contacts to most of the devices. Good control on the film deposition. But the main disadvantage of this is that low vapor pressure are difficult to deposit. It needs material heating, and the material stoichiometry in compounds or alloys deposition is difficult. Then the electron beam deposition, that is, in electron beam heating technique, heat is produced by high energy electron beam bombardment on the material to be deposited. Here, high energy electron beam is used. Here you can see, this is the schematic diagram of electron beam evaporation. Here we can see that is high energy electron beam is used to evaporate the material. Evaporation material is here in the crucible, and this electron beam is produced by some electron gun, which uses the thermionic emission of electrons produced by an incandescent filament. And emitted electrons are accelerated by a high voltage potential. Here you can see, here these emitted electrons are accelerated by a high electron voltage potential, and then it will be deposited. Here magnetic field is also used to just bend down the electrons, bending of the materials towards the substrate. To bend the electron trajectory, allowing the electron gun to be positioned, and it is possible to obtain localized heating because of electron beam. So electron beam, that is possible to obtain localized heating with a high density of evaporation power, and high melting point materials like tungsten, tantalum, carbon can be deposited through this electron beam evaporation. Here the main advantage is, that is, the bombarded electrons kinetic energy is transferred to the source metal atoms, so which causes the local melt, and because of that it avoids contamination from the container. There will be no contamination from the container. It ensures high quality deposition with reputable accuracy and growth under high vacuum with cleanness. But the disadvantage is that here energetic electrons are used, so that may damage thin film surface. And also it is expensive in comparison to resistive heating due to additional electron beam assembly. But some high melting materials, but why will you use this if it is expensive? Because of this high melting materials, that is tungsten, tantalum, carbon, those cannot be used in there or in resistive heating case. So next is your pulse laser deposition. Pulse laser deposition technique, where a high power laser pulse laser beam is focused. Here you can see laser beam that is focused on the target material, and here you can see that is used on the high energy pulse laser beam is focused inside a vacuum chamber to strike a target of the material that is to be deposited. And this material is vaporized from the target. Here you can see one plasma plume is created when high energy laser beam is focused on the target material, here it is vaporized and form a plasma plume, and that is again that gets deposited. This vaporized material will get deposited on the substrate surface. And this is the sample holder. It is high vacuum also used. Also sometimes it is some reactive gases are also used. That is oxygen also used here. This technique is broadly employed to deposit alloys, compounds, oxide materials, multi-layers due to its excellent stoichiometry transfer. Here, the stoichiometry of the target, whatever is the stoichiometry of the target, that film stoichiometry will be exactly similar. And this process can occur in ultra-high vacuum or in the presence of a background gas such as oxygen, which is commonly used in depositing oxides to fully oxygenate the deposited films. This is the schematic diagram, as I told, that is here the laser beam is falling on the target material and a plasma plume is created, and again the material getting deposited on the substrate. And the advantages of a pulse laser deposition is it is simple, that is fast and easiest way to study new chemical systems, compatible with oxygen and other reactive gases. The film thickness can be controlled by tuning deposition parameters, and the high crystallinity. Here the film is in high crystalline form, and it provides precise transfer of stoichiometry from target to substrates. But the main disadvantage is it is non-uniform and difficult scale up to large wafers. Arc evaporation. Next is your arc evaporation. It is also a physical vapor deposition technique in which the electric arc to vaporize the material cathode target. Here you can see this is the electric arc is used to vaporize the cathode material, and the vaporized atoms again gets deposited. These are all physical vapor deposition. That means we have the target material, and from that vapor will be created by using different techniques. Sometimes sometimes laser, sometimes arc, sometimes heating element, like that. So here arc evaporation is also a physical vapor deposition technique. So the vaporized material then condenses on a substrate, forming a thin film. This technique can be used to deposit metallic, ceramic, and composite films. The arc evaporation process starts with the striking of a high current, low voltage arc on the surface of a cathode that gives rise to a small, highly energetic emitting area known as a cathode spot. Again, that cathode spot is extremely high, which results in a high velocity jet of a vaporized cathode material, leaving a crater behind on the cathode surface. Then again, that arc, it is generally that cathode spot is only active for a very short period of time. It is self-extinguishes and again reignites in a new area. So here the arc, it seems that arc is moving on the cathode surface, and accordingly your films is getting deposited on the substrate surface. A wide variety of thin proteins can be synthesized, like your titanium nitride, titanium aluminum nitride, chromium nitride, zinc, zirconium nitride, hard coating materials. Next is your molecular beam epitaxy. This MBE, that is a highly specialized technique. Molecular beam epitaxy technique for producing epitaxial structure with monolayer control in an ultra high vacuum. MBE involves directing atomic or molecular beams onto a heated substrate to form epitaxial layers. Here you can see, this is the schematic diagram of MBE setup. Here we can see that is some Knudsen effusion cells are there, where the target individual element are placed, and when the temperature of these elements reaches the melting point, then the vaporized atom will start deposited here. It will be vaporized. These effusion cells contain individual element to be deposited on the substrate surface, and heating will take place. And here there is rotating sample holder. Here the sample holder is rotated so that a uniform deposition of the film can be obtained. You can see that it is a high vacuum, ultra high vacuum is used here. This is the airlock valve and sample transfer unit, ionization chamber, reed, electron gun. Here, reed is used to check the film deposition process. In this case, here generally there is no carrier gases is used, as well as ultra high vacuum. So it results in the highest achievable purity of the grown films. This technique is used in the construction of quantum wells, dots, and wires for use in lasers. These are also used in heterojunction bipolar transistor for use in satellite communication and electronic optoelectronic devices. And the main advantages are the films are high quality films are produced. High quality films are produced. And it has good control over layer thickness and composition. It allows extremely thin films to be fabricated in a very precise, carefully controlled way. But the main disadvantage is that it demands ultra high vacuum environment. And it's a slow and laborious method, which means this method is only suitable for these scientific research laboratories. And the equipment involved is complex and very expensive because of difficulty of achieving such clean and high vacuum conditions. Next is your ion plating. Ion plating, it is again a physical vapor deposition process that utilizes ion plating. That means that utilizes concurrent or periodic bombardment of the substrate. Here, what happens? There is periodic bombardment of the substrate will take place, and then deposition will also take place. Here, this target material that can be produced or vaporized by E-beam evaporation, thermal evaporation, and here I got here it is the substrate will be bombarded with some ions. Here, that means that is there will be periodic bombardment of the substrate and depositing atoms of film material by atomic size energetic particles. Bombardment prior to deposition. First, the substrate surface will be bombarded. So that prior to deposition, it is used to sputter clean the substrate surface. And bombardment during the initial deposition. See, here it is, that is concurrent or bombardment of the substrate. So first, the bombardment before deposition, that is used to sputter clean the substrate. And bombardment during the initial deposition phase can modify the nucleation behavior of the depositing material. And during deposition, the bombardment is used to modify and control the morphology and properties of the depositing films. For best results, the bombardment be continuous between the cleaning and the deposition portions of the process in order to maintain an atomically clean interface. The depositing material may be vaporized by evaporation, sputtering, or arc vaporization. Here, this depositing material, that is the target material, that can be vaporized by using various techniques. So here also we can see that is the thin film material. Other techniques are also used in some techniques. And the main advantages is better surface coverage than other methods. And the sputter clean the surface and maintain it clean until the film begins to form. Chemical reactions when supplying plasma and energy to the surface of the bombarding species. Here, the more energy available on the surface of the bombarding substrate, resulting in more complete bonding. Because of the bombardment of the substrate surface, more energy is available to the surface of the bombarding species, resulting in more complete bonding. But the main disadvantage that here more increased variables are taken into consideration. So compared to other techniques, uniformity of plating is not always consistent. Excessive heating to the substrate because bombardment will take place as well as deposition will take place, and this process is costly and time consuming. Next, another technique, that is the sputtering technique. That is mostly used for depositing metal and oxide thin films and high melting point material. That is sputtering technique that is mostly used for depositing metal and oxide thin films and high melting point materials. Here, in this case, argon ions are created by glow discharge under vacuum. You can see argon ions are created by glow discharge under vacuum, and those argon ions are used to sputter out the target material for thin films and these target atoms or molecules adhere to the substrate and form thin films. Here, argon ions are used to sputter the target material, and these target material sputtered target material are getting deposited on the substrate surface to get the films. That sputtering steps, as I told here, you can also see in more general way, that is sputtering gas here, and argon ions will be created, and those will be directed at a target surface, and the ions sputter target atoms. The ejected atoms are transported to the substrate surface, then atoms condense and form a thin film. This is the magnetron sputtering. In this case, it is also one type of a sputtering. That is here, in this case, what happened? There is interaction between the magnetic field and electric field. So this causes the electrons to spiral. Here you can see the electrons. These dots are the electrons, and this is the argon gas atom and argon plus ions. Yellow color, that is the argon plus ions, and the green color, that is the argon atom. What happens due to the interaction between magnetic field and the electric field, that causes the electrons to spiral in the vicinity of the target surface. This increases the probability that electrons will strike the argon gas. This increases the probability that the electrons will strike the argon gas, and that will generate the ions. The generated ions collide with the target surface under the action of an electric field to sputter the target. Here same principle is also used, only the difference is magnetic field. And magnetic field and electric field, there will be interaction between those two. So that electrons will spiral around the vicinity of the target atoms. Again, this magnetron sputtering can be of DC sputtering or RF sputtering. In DC sputtering, as you know, DC power is used, and RF sputtering, RF power is used. And this DC sputtering, that is generally used with electrically conductive target material. And RF sputtering uses RF power for most dielectric materials. This is used for dielectric materials, but we can see aluminum nitride film. That is both DC and RF sputterings are used. But by using DC sputtering and RF sputtering, we can compare the film properties and which one will be more useful, depending on our application. Here, the advantage of sputtering, that is, high melting materials can be easily found by sputtering. And the deposited films have composition similar to the composition of target material. The sputtering sources are compatible with reactive gases such as oxygen. And the main disadvantage is thick coatings cannot be obtained, and it is difficult to deposit uniformly on complex shapes. Next is chemical vapor deposition. This is one important chemical deposition method. This chemical vapor deposition, that is the CVD. In this case, what happens? The substrate is exposed to one or more volatile precursors. Here we can see that is the substrate is exposed to one or more volatile precursors, and these precursors react on the substrate surface. And the reactants, these precursors will react with the substrate surface, and then the reactants will be adsorbed on the substrate surface and form the film. Here you can see this, these are the mass flow controllers, where these mass flow MFCs are used to introduce precise amount of reactant gases into the reactor chamber. Here you can see the furnace and substrate here. Chemical precursors are used, and carrier gas sometimes. This is also, that is hydrogen. Nitrogen is used for purging. Hydrogen is also used as carrier gas, and other things are also used. Other gases are also used. Sorry, carrier gas, that is nitrogen, and reactive gas, that is hydrogen, is also used. So that also depends on what kind of material we are depositing. You can see that is, the reactants are then transported to the substrate surface where the chemical reaction takes place, and the substrate adsorbs the desired reaction product. Any additional chemical byproducts are dissolved and removed. Here you can see. That means suppose we want to deposit silicon carbide on silicon substrate. So here we can use silane and methane, that is for as reactive gases SiH4 or CH4, and those will react on the substrate surface, forming silicon carbide, and other byproducts will be just taken out through the exhaust. The advantages of this CBD technique is high growth rates, good reproducibility, and epitaxial films growth also occurs, good film quality, and conformal step coverage. That means here epitaxial films can also be formed. That means that is the oriented growth. If the substrate is 100, then we can also produce 100. That is the orientation. And a high growth rate and good reproducibility. And the main disadvantage is that it is a high temperature process and a limited range of materials, because that precursors should be available for chemical reaction to take place inside the chamber. And the use of, the main disadvantage is use of flammable, toxic, and corrosive precursor gases make it unsafe. It is difficult to deposit multi-component compound. This plasma enhanced chemical deposition. This is also another chemical vapor deposition process used to deposit thin films from a gas state to a solid state on a substrate. This is also one type of CBD technique. But here what happens? In this case, chemical reactions are involved in the process, which occur after creation of a plasma of the reacting gases. Here plasma first is created. This plasma is generally created by radio frequency or direct current discharge between two electrodes. And here we can see that is the precursor gas. Here this precursor gas is fed to the RF here through some shower head. Here this shower head itself is used as one of the electrode, and precursor gases are inside this plasma, and they react with the plasma, and these atoms and molecules, they react, and once the shower head and the chamber walls are cooled and the substrate is heated to promote heterogeneous surface reactions. Sorry. This thin films is formed under a relatively low temperature. Here the precursor gas is fed to the chamber using a shower head arrangement. As I told, that is here this shower head. This is the shower head through which the precursor gas is fed to the chamber. Precursor entering the plasma undergoes electron molecule collision, producing high energy excited molecules and molecular fragments that adsorb on the substrate surface and deposit the film. PCBD is widely used in the production of solar cells and microelectronics. Again, this low pressure chemical vapor deposition, that is also another CBD technique that is performed at pressure of 0.1 to 10 ranging from 200 to 800 degrees centigrade. The reactants are added to the chamber using a specialized precursor delivery system shower head. Here also a specialized system delivery shower head system is used. Here you can see that is wafers are here. That is used low pressure but high temperature. High temperature, that is here, and in this case taking place, there is no plasma here. Our shower head and the chamber walls are cooled and the substrate is heated to promote heterogeneous surface reactions. Once the reaction is complete, the byproducts are removed using the vacuum pumps. LPCVD is most commonly used in the production of resistor capacitor dielectrics, MEMS, and anti-reflective coatings. Mostly used for the deposition of polysilicon films, that is done using SiH4 in the temperature range 600 to 660 degrees centigrade, and also for deposition of nitrates. Here we can see that is the difference between this LPCVD and PCVD. Both are CVD process, but LPCVD, that is low pressure CVD, that has a higher temperature than PCVD. But PCVD uses plasma to energize the reactants. LPCVD uses a hot wall tube reactor environment to provide energy to the reactants. The plasma in PCVD allows for a more controlled and a lower temperature deposition process. LPCVD primarily uses silicon-based films and also silicon nitride films. That is typically deposits silicon nitride films. But produce both polymerized and tungsten films. Again, another technique, that is ALD, atomic layer deposition technique. That is also another chemical deposition technique. And this technique is based on the sequential deposition or sequential use of a gas phase chemical process. That is here sequential use. Sequential use means, suppose we have, mostly we use two reactants or two precursors. Mostly the ALD generally use two precursors, and these precursors react with the surface of a material one at a time. That means, suppose here precursor A, that is first used, then what happens, that is first pulse of reactant A will be given to the substrate, then purging will take place. Again, second reactant will be given, that is reactant B will be given, and purging will take place. Self-limiting, that means it is a self-limiting process. That is ALD. It's a most important point here is it is sequential and self-limiting. That means once the reactant side, the reactants, that is that process ends. Reactant react with the substrate surface. That process ends once it is depleted. That means the first atom or molecule gets deposited on the substrate surface, then the reaction stops. That is the self-limiting. That is self-saturation will take place. After that, another reactant will be given to the process. ALD is a CVD technique also that is suitable for inorganic metal layer, that is oxides, nitrates, and some metals. A thin film is slowly deposited through repeated exposure to separate precursors. And parameters here are, that is the reactants, substrate, and the temperature. These three things are important. And the main advantage of ALD technique is, that is low temperature processing, high quality films, and scalable to large substrates, and batch processing. And that quality of the films is associated with a self-limiting growth process. And conformity and atomic level composition control. But the disadvantage is it is time consuming, low effective deposition rate, because only one layer can be formed, and a costly method also, and very high material waste rate also. This is the sol gel technique. Next, another technique, chemical technique, that is the sol gel technique. That is one of the best weight chemical technique. Here sol means a colloidal suspension formation, and gel means the transformation of sol to viscous gel. A sol gel process occurs in several steps, that is hydrolysis and condensation of molecules. First step is hydrolysis. Hydrolysis means that is the reaction will take place, or a chemical reaction will take place. Water is the main solvent here. Water will be used to break the chemical bond between the precursor material, so that there will be some reaction of water, and that reactant or a precursor material will be soluble. Either it will be soluble or it will form some precipitate, or it will not be soluble. That depends on the reactant material. So first hydrolysis will take place, and then condensation of molecules will take place. Then sol formation will take place, gelation, aging, and drying. Here you can see the schematic. That is hydrolysis. Here SiO2 formation from silicon alkoxide. We can see that is hydrolysis process. Water will be taken. Here some silicon methyl group is there. Here we can see SiOR, that is some methyl group, alkoxide group is here. That during hydrolysis, this breaks the bond. That means water breaks the bond between the methyl and OH group. It forms silicon hydroxide. Then condensation means that is silicon hydroxide. Those will condense, forming SiO2. Sol formation will take place. Then jellification will take place. Gel means that is some kind of solid matter. It will not solid, but it is in between the sol and solid form. And then gel formation will take place. This, another thing is that is this sol gel technique generally uses two processes. That is spin coating technique and deep coating technique in producing thin films. That is, first the sol gel product will not form. That is, sol gel reaction will take place. Then those material will be used for producing films. That is, used spin coating and deep coating are used for producing the films. These are the main advantages of sol gel technique. That is, that used to prepare materials of various shapes, such as porous structure, thin fibers, dense powders, and precise control over the doping level, and no need for special or expensive equipment. But the disadvantage is preferential precipitation of a particular oxide during sol formation due to the different reactivity of the alkoxide precursors, and shrinkage of a wet gel upon drying, which often leads to fracture due to the generation of large capillary stresses. Here it is the spin coating technique. Here it is a rapid diffusion technique. You can see that is this actually there was some videos, but I don't think it will be possible. So this sol gel technique, spin coating technique. In this case, what happens? The equipment has a chamber where a substrate is being held firmly by rotatable feature that uses vacuum to hold the substrate in place. The coating solution is introduced onto the substrate surface. Here you can see the coating solution is introduced on the substrate surface. This here it is the here you can see the substrate, and that is substrate holder is there, and it is inside a chamber where vacuum is created, and this vacuum is there to hold the substrate on this chuck. In this chuck, the substrate is held, and substrate deposition material is spread on this substrate, then spin up. The spin means the rate of spinning will increase, then spin up, that will decrease, then solvate, that film will be formed and solvate evaporation will take place. This is the schematic diagram of thin film formation. Actually one video was there, but it is not opening, so I am not able to show that video, how the spin coating takes place. The rotation of the substrate at high speed means that the centripetal force combined with the surface tension of the solution pulls the liquid. Actually here what happens, that there will be rotation of the spin coating, that will spin at high speed. That depends on the revolution per second. That is also depends on how much speed we need. That means, and depending on different speed rate, also the material properties will also vary, and the material thickness will also vary. So depending on that, we will see that that is the rotation of the substrate at high speed means that the centripetal force combined with the surface tension of the solution pulls the liquid coating into an even covering. Final film thickness and other properties will depend on the nature of the coating, that is viscosity, drying rate, percent solid, surface tension, etc. And the parameters chosen for the spin process, such as the rotation speed. These are the advantages. That is, it is a very simple and low cost way to batch process individual substrates compared to other methods. Here again, it is an advantage, but at the same time, disadvantage is that it is a single substrate process. It cannot be for roll-to-roll processes. And the ability to have high spin speeds leads to fast drying times. Fast drying times, because of that, there won't be any need for post-deposition heat treatment. But again, here this is one advantage for some material, another, but it is also disadvantage to some other material which require time to self-assemble or crystallize. That is for particular nanotechnologies. And another disadvantage is that is the wastage of material. Again, deep coating. This is spin coating and deep coating generally results from sol gel technique. Deep coating is a simple, low-cost, reliable, reproducible method which involves the deposition of a wet liquid film. Here, what happens? The substrate will be immersed into the solution. Here we can see the precursor solution is here. Substrate will be immersed. Then nucleation will take place, and coating will take place on the substrate surface, and the substrate will taken out at a constant speed. That is mostly depends on the speed of the taken out the substrate. So this process, deep coating process, that can be separated into 3 different stages. That is, as I told, that is immersion and a dwell time. Dwell time means that is the interaction time of the substrate with the coating solution. Interaction time of the substrate with the coating solution for complete wetting. And then deposition by pulling the substrate upward at a constant speed, a thin layer of a precursor solution is entrained. That is, film deposition occurs. Then evaporation, the solvent evaporates from the fluid as deposited thin film, which can be promoted by heated drying. Subsequently, the coating may be subjected to further heat treatment. You can see that is here coating take place, and this is your sol-gel reaction here occurs, and in this precursor solution, substrate will be dipped. So easily, that's why it is called deep coating. And the advantage of this deep coating, it is the simple, reliable, and powerful option capable of coating almost any substrate material. But the disadvantage is unbalanced coverage. Here the coating, that is not fairly uniform. Unbalanced coating will take place, varying thickness across the surface of the material, and process is slow. Here we can see that is the another chemical deposition technique, that is CBD, that is you can say chemical bath deposition. Here again, that is, it is the cheapest method to deposit thin films and nanomaterials. Chemical bath deposition, that is the cheapest method. And this method involves controlled precipitation from solution of a compound on a suitable substrate. Here also you can see this is the chemical bath deposition technique. Here the substrate is here, that is the substrate is inside the chemical bath. Heater is there, and the thin films is deposited. That is chemical precipitation. Precipitation will take place on the substrate surface. Substrates are immersed in a chemical bath containing precursor solution. Film thickness and deposition rate are controlled by varying the pH of the solution, temperature, reagent concentration, etc. CBD has the ability to coat large areas in a reproducible and low-cost process. A wide range of chalcogenide and chalcopyrite materials have been prepared by CBD technique. And the advantage is that is here, it only requires the solution container and substrate mounting devices. It yields stable, adherent, uniform, and hard films. It is one of the suitable methods for preparing highly efficient thin films in a simple manner. And the major drawback of CBD technique is the inefficiency of the process is that it is in terms of the utilization of starting materials and their conversion to thin films. That means what starting material, that is the precursor material we use, that is the whether it will be precipitated on the substrate surface or not. That is the main important point, drawback. And wastage of solution after every deposition. Substrate cleaning is very important factor in obtaining good adherent films. Spray pyrolysis. It is again a very simple and cost-effective technique that is used to prepare thin and thick films. Spray pyrolysis, generally, it consists of an atomizer here, spray pyrolysis. It consists of an atomizer, precursor solution, hot plate, and temperature controller. Here you can see atomizer in which that is liquid solution is there, and you know how the way it will spray out on the substrate surface. The atomizer in the spray pyrolysis technique is used for the formation of a stream of the liquid which has to be coated over the substrate. And the droplet size of the precursor solution depends on the method of atomization. And the substrate is heated over the hot plate for the coating. the deposition, most important parameter here is the deposition temperature and the droplet size are the two most important parameter that control the surface morphology and thickness of the film. This technique is very frequently used for oxide and chalcogenide materials deposition. And the advantage is this is low cost setup, simple and rapid film growth rates, and potential for mass production and reproducibility of the films. But wastage of a precursor metal during spray coating is the main demerit of this material. Plating, that is another technique. Plating, you must have heard, that is plating. Some plating occurs generally. This is depositing a thin layer of one metal onto the surface of another metal. Here, this plating is different from other techniques. That means here, two metals are used for plating. The one metal is plated by some other metal. That means the metal will be used as the target as well as the substrate, and metal will be used as the reactant species here. So here plating is done to improve appearance of the metal surface and protect from corrosion. And this plating can be of two types. One is electroplating, another one is electroless plating. Electroplating and electroless plating. In electroplating, generally, what happens, that is externally applied electric current is used to deposit a layer of metal onto the surface of another metal. While electroless plating utilizes chemical reactions to deposit a metal coating on the surface. In electroplating, that is, you can see here, is used. Electroplating, here we have two electrodes and electrochemical cell is used. We have two electrodes, one is cathode, another one is anode, and cathode material on which metal will be deposited. This is the metal on which metal will be cathode material. That is the metal on which metal will be deposited, and anode is the metal that to be deposited on the cathode. Here the chemical reaction takes place, and by applying some current through it. In this, actually what happened, when an electric current flows through the circuit of the electrochemical cell, the electric current oxidizes the metal atoms and dissolves them into the electrolytic solution. These dissolved atoms of metal are then reduced at the cathode and deposited on it to form a thin layer. The thickness of the layer deposited can be controlled by varying the current plating time and concentration of electroplating is widely used in manufacturing of decorative items, jewelry, corrosion resistant objects, etc. And in this electroless plating, you can see here there is no electric current. Here only the aqueous solution is there, workpiece, that means the substrate is here and ions of a plating material is there. That is, ions are getting deposited here. In electroless plating, that is, there is no electric current. Has to be coated, that is, metal surface has to be coated, is thoroughly cleaned, and it is immersed in an activation solution to provide adhesion of the metal coating. It consists of the bath chemical solution having metal ions of the metal that has to be deposited on the substrate. The cleaned and activated substrate is immersed into the electroless plating solution, where the chemical reaction is initiated by the reducing agent present in the solution. This plating reaction allows a thin metal coating to be deposited into the surface of another metal. Here reaction is taking place. And electroless plating is very commonly used in applications that involve complex geometric shapes, even thickness distribution of coating layer and coating of non-conductive metal surfaces. And now all these are, whatever I discussed, these are different techniques used for thin film deposition, and that was the main aim of this talk. Different techniques are used, and now we will see that where these thin films can be applied. That is, here we can see, as I already discussed in the first slide, that is the thin film solar cell, that is photovoltaics application. Thin film batteries. These thin films are used in batteries, in solar cell, in transistor also. This thin film solar cell, here you can see, that is, this is In this case, as I told, that solar cell is a p-n junction, and p-type material, that is bottom p-type observer layer formed by second semiconductor material, and top n-type window layer formed by first semiconductor material. And all these are in thin film form. Most important is thin film, and these thin films are deposited by using these different techniques. So we can see this, that is in solar cell, this thin film technique is utmost of importance, because thin film solar cells can provide us maximum efficiency. That is the conversion of solar cells generally converts, that is solar energy to electrical energy. So in order to get maximum efficiency, these thin film solar cells are used. That means these advantages of thin film solar cell, advantages of this thin film, that is higher resistance to degradation, lower thermal losses at extreme temperatures due to the low temperature coefficient, and high efficiency for most technologies, that is cadmium telluride, copper indium gallium selenide, and especially gallium arsenide. That is gallium arsenide. Actually what happened, this CIGS that is used have efficiency, theoretical efficiency of 33%, and this cadmium telluride also theoretical efficiency is high, but research is going on to obtain that theoretical efficiency. At most now it is cadmium telluride case, that is 22.1%, and gallium arsenide, that is 39%. But it is very difficult to get this gallium arsenide thin films that is used for that is space applications. And these thin films are generally ideal for portable and BIPV application. BIPV application means that is building integrated photovoltaic applications. Building integrated photovoltaic applications. And this is suitable for high efficiency space applications with CIGS and gallium arsenide photovoltaic modules. Promising research and development with much more ground to cover. This requires less material to create photovoltaic modules. Thin film solar panels are lighter than crystalline silicon photovoltaic modules. Generally, silicon is used. You must have heard silicon solar cells. Silicon is used for most of the solar cells. But nowadays, other materials are used in thin film form in solar cells. This is again another thin film application that is used in battery. Here you can see this cathode. In battery, we have cathode, anode, and electrolyte. These are the layered materials. These are the layered materials. Those are getting again deposited by thin film deposition techniques. My aim is to show where these thin films are used. So here we can see this thin film battery application. Mostly you must have heard that is lithium-ion battery. That is rechargeable battery, and those are used in mobile phones and laptops. But thin film battery, superior choice over lithium ion. They are thinner and lighter without sacrificing voltage or current. This cathode, anode, and electrolyte are layered materials often deposited by physical vapor deposition like thermal evaporation and sputtering. That means again thin film deposition techniques are used to form this battery, this thin film batteries. And these are in narrower form, here cathode and anode. These narrower proportions are ideal for use in complex electronics like ultra-thin laptops. Another application for thin film batteries is in the healthcare industry, where they power implantable medical devices. Again, these thin film are used for optical coatings that include, that is your anti-reflective coatings, anti-ultraviolet or infrared coatings, and anti-scratch coatings. You can see here that is sunlight. Sunlight consists of ultraviolet radiation and other radiation also. So here, because of this thin film, this allows visible light to enter the house or your car. But it rejects, because of these thin films, it rejects the heat and ultraviolet radiation. Again, here anti-reflection coating, that means that minimize the reflection, that is used to destroy the hazards created due to the reflection. So here, these thin film coatings are used as anti-reflection coating, anti-ultraviolet or infrared coatings, and anti-scratch coatings. These are again used, these thin films are used as corrosion resistance. That means you can see that due to this thin film coating that reduces rust and degradation in pipes, engine parts and bearings. That means here we can see corrosion is a significant challenge to most of the industries in the world. It causes disasters and massive. So thin film coating can be used as corrosion resistant. In biomedical also, that means you can see it is used for long-term coatings. That means you can see that it's medical implants such as artificial limbs or joints and implantable sensors such as pacemakers must be properly treated with coatings appropriate for long-term exposure to human tissue and biological material. These thin films are used to perform a dual role in protecting both the device and the person. Thin films are used for a drug delivery. Thin films are also used for tissue engineering substrates. These are biocompatible coatings, that is protein repellent coatings as well as antimicrobial coatings. These are used like this. And final thought on thin film application. You know, thin film applications are so numerous in everyday life that it is hard to for any industry to think which does not rely on the this thin film advanced technology. They have a practical uses in almost every sector, from healthcare and memory chips to electronics and solar energy. Thank you. Thank you.
Thank you, ma'am. We'll have a short question answer session.
Yes.
Participants, if you have any question, kindly write it on chat. Anybody has any query, please write on the chat. We'll wait a few minutes, ma'am.
Yes, no problem. I will invite the questions.
Or you can raise your hand if you have any question. Participants, if anybody has any query, you can write on the chat box. We'll answer your queries. Ma'am is going to answer.
નેક્સ્ટ સેમેસ્ટરમાં નેક્સ્ટ બીઓએસ માં છે કદાચ રિઝલ્ટ કરવાનું છે એટલે તમે ઉતાવળમાં બનાવ નહીં કરવું કે નહીં બનાવવાનું એવું તો નહીં છે એટલે તમે લોકો બનાવી નાખો તો એવું તમે તમારે જે તે ટાઈમનું કામ નથી સબા
ITOs, please mute Hina Ben. ITOs, please mute Hina Ben.
ઇલેક્ટ્રોનિક્સ માં માસ્ટર તો છે મસ્ત કરે છે લગભગ ઇલેક્ટ્રોનિક્સ સરસ બનાવે છે.
Manisha ma'am, can we conclude?
There is no question?
Still not, ma'am. There is no question on the chat box.
But ma'am,
ma'am, there's one question.
Yes. I am not able to hear you. Hello?
Yes, ma'am. Which method is very appropriate for making biopolymer and also metal oxide thin film?
For metal oxide thin films, generally that sol gel technique is used, and metal oxide also we can use thermal evaporation technique. And I have discussed all these techniques. That depends on the application area. And biopolymer, that is, if it is thin films, that is biopolymer, generally we can use this spin coating, or you can use deep coating also. Because this thermal evaporation or E-beam evaporation, that is physical methods, there we cannot use Those physical vapor means physical deposition technique we cannot use, but chemical technique we can use depending on the precursor material. Which technique will be used, that depends on the precursor metal, what precursor metal we have, and on what substrate it will be deposited. That also depends, because temperature is also a factor. So that depends on various factors.
Thank you, ma'am. We have next question. For preparation of CuO film, which method is suitable?
Copper oxide.
Yes, ma'am.
That CuO film that we can deposit, that is sputtering technique can be used mostly. Sputtering technique.
We have next question. How do the thickness and uniformity of a thin film impact its properties?
Thickness and uniformity. Okay, that uniformity, that means if it is uniform, then that affects the electrical behavior a lot. Electrical behavior, if it is not uniform, that means somewhere it is not deposited, or higher thickness or lower thickness, then the electron transfer, there will be problem in electron transfer. So that affects a lot. Electrical behavior will be affected very much, and uniformity, because of that we can have also some other properties like optical behavior also matters. If how much it is thick, that depending on that thickness, when light falls on the substrate, on the film, how much it is getting reflected back, transmitted, or how much light will be absorbed, that also depends that on the thickness of the material. Optical both electrical and optical properties will matter. Means thickness and uniformity will affect the optical and electrical behavior.
Thank you, ma'am. Next question is, if we want to measure thickness of film, thin films, what is to be used?
Actually, in some techniques, in like thermal evaporation technique, E-beam technique, some crystal monitor is there inside that chamber, where the thickness can be measured simultaneously during the deposition process. But if the film is outside, that means by taking it out of the chamber, we can measure it by surface profilometer. Surface profilometer is there. Another technique is also that ellipsometry technique is there. Through this technique, we can measure the thin film thickness.
Thank you. And next question is, how does the choice of substrate affect the deposition process and the quality of the thin film?
Yes, substrate matters a lot. If it is, suppose, as I told here, metal substrate is there, then some metal will be deposited. If it is semiconductor substrate, then we will deposit on, see, substrate surface preparation is very important. If the substrate surface cannot be prepared properly, then film deposition will not take place. Even if it will take place, that will not be uniform. So surface, substrate selection is very important. And also in thin film and epitaxial film also, if it is epitaxial growth, you will see that a substrate matters a lot. There will be lattice mismatch like that. But if it is just metal contacts like that, so whether that film will be adhered to the substrate, that depends on the substrate, and that is you can say that is one is lattice mismatch, another one is that is substrate and film material wetting properties, whether it is properly wetted on this substrate, that is your solution process, that also depends. So this thin film deposition technique mostly depends on substrate. We cannot deposit all the materials in all the substrate. That is very specific for which application you are using. Suppose we are using very thin films, that is molecular beam epitaxy. Suppose molecular beam epitaxy, we cannot use any substrate to deposit any material. That is very special technique. Similarly, thermal evaporation techniques, we have to use that kind of substrate. We cannot use there in glass substrate. Suppose substrate that if the temperature is high, then we cannot use glass substrate. That suppose we cannot use polymer substrate. we cannot use that substrate also. That temperature is also a factor. At the same time, that substrate should be properly aged so that bonding will take place. Most important is bonding between the substrate surface and the film material. If bonding is not proper, then film will not be deposited. So it mostly depends on the substrate.
We have next question. Thank you, ma'am. How could we differentiate thin coating and metal adoption method? That is by adding some metal on surface by using mechanical process, and which is more effective in terms of mechanical properties.
I'm not getting the point actually. What are you asking?
Ma'am, how could we differentiate thin coating and metal adoption method? I think
Metal adoption, what is that?
and
Metal adoption, I don't understand actually.
and
What he means?
by metal adoption, he means by adding other metal on surface by using mechanical process.
Mechanical process means here we are using plating. That is metal on metal. On other mechanical process, how the way you can deposit thin layer. Thin layer means here that is the proper bonding between two materials. Otherwise, there will not be deposited. It will just come out. Film will be properly deposited on the substrate. So there should be some bonding between the substrate material and the film material.
Thank you.
We cannot use like that some mechanical process to deposit it like that.
Next we have, can we use CVD for a transition metal dicalogenicides like selenium, like selenite, sulfur, etc.? Or which method is very appropriate for making TMDCs? The question is, can we use CVD for a transition metal dichalcogenides like selenite?
Dichalcogenides. Okay, this dichalcogenides and the dichalcopyrides, those are generally those are used. You can use, that is your one technique is there. I have already told that technique. Oh, sorry. What I did.
We can hear you, ma'am. No issues. We can hear you.
Okay. So CBD technique, that is CBD technique, that is mostly used if the precursor reactant gases are available for deposition, then we can use it. At the same time, what is the temperature of reaction? That is also important. So for high melting materials, we can use high temperature. But if this sulfur and that chalcogenide material, that is not possible by CBD techniques. That is used for, I think, ALD technique, I have already discussed that. That is used for chalcogenides and chalcopyrite materials.
Same participant Shailja is also asking which method is very appropriate for making TMDCs.
TMDCs, that is transition metal dichalcogenides. That is transition metal dichalcogenides. I am not sure about that actually. Maybe I have seen that is if proper precursor material is used, then we can use sol gel technique if it is used. If it is precursor material is available, then we can use.
Thank you, ma'am. We have next question for cerium oxide gas sensor and humidity sensor. Which type of films should be used and by which technique?
For gas sensor?
Yes, cerium oxide gas.
First, which oxide gas sensor?
Cerium. CERIUM. Cerium, I think so it is pronounced.
Cerium. For oxide materials, you can use, that is thermal E-beam evaporation, you can also use for oxide materials. And for gas sensor, for gas sensor, that uniformity of the film material is very important. Because there we are using the electrical properties. So uniformity of the thin film is very important. So we have to take into consideration of that first. Then we will see whether it is properly deposited or not. That is, you can use high melting material. If it is high melting or oxide materials, that is, we can use, that is your thermal evaporation method or sputtering method. Sputtering we can use also oxide materials.
The last question, ma'am. Is thermal evaporation method suitable for zinc oxide synthesis?
Yes, I am not getting actually what you told.
Is thermal evaporation method suitable for zinc oxide synthesis? ZNO
For zinc
synthesis?
oxide,
Yes.
it actually thermal evaporation method is also used for zinc oxide synthesis, but you can use for suppose in thermal evaporation it may give your amorphous type of films also, but mostly PLD is also used for zinc oxide. PLD for highly crystalline material, zinc oxide you can use, but it is very difficult to get zinc oxide thin films by PLD. Of course, thermal evaporation is also used for zinc oxide.
I think that's all from question answers. Thank you so much, ma'am. Thank you, ma'am, for such an enlightening session on thin films. You rightly started from basics of what is thin film to processes, explaining process in detail, then giving very what I would say day-to-day life examples like solar panels, battery solar panels, then thin film coatings, etc. So I hope the knowledge which you have shared with our participants is going to help them in their future endeavors. And thank you very much for sparing a wonderful time with us and sharing your knowledge with us. Thank you so much. So with this, we end the pre-lunch session. We'll have post-lunch session at 2:15. Thank you very much, everybody.
Thank you, ma'am.
Thank you.
Thank you, ma'am. We'll be in touch with you. Thank you so much.
Thank you very
Okay.
much, ma'am. Thank you very much.
May I start, sir?
Yeah, sure. Sure, start.
Good afternoon, everyone. Welcome to the post-lunch session of second day of one-week national workshop on advanced synthesis and characterization techniques organized by Department of Applied Physics, Amity School of Engineering and Technology, Amity University, Madhya Pradesh. For this session, we have with us Dr. Pankaj Srivastava from ABV IIITM. I would like to first introduce Sir. Dr. Srivastava is currently Professor and Head of the Department of Applied Sciences in ABV, Indian Institute of Information Technology and Management, Gwalior. He received MSc degree in Physics with specialization in Material Science from School of Studies in Physics, Jivaji University, Gwalior in 1992 and worked as Research Fellow in Theoretical Condensed Matter Physics Group at International Center for Theoretical Physics, Trieste, Italy during 1995 to 1996. He was awarded PhD degree from Physics Department, Central University, Allahabad, Prayagraj in 1990. From October 1998, he has worked as a research associate in ISRO and UGC-sponsored research projects at Physics Department, Central University of Allahabad till February 2003. He started his academic journey as a lecturer in the Applied Physics Department, Madhav Institute of Technology and Science, Gwalior in March 2003. He joined as Assistant Professor in Applied Science Discipline at ABV IIITM in October 2006, was designated as Associate Professor in October 2009, and became Professor in February 2019. He has more than 21 years of teaching and research experience. To his credit, he has expertise in theoretical modeling and simulation in material science. He has been working since last 24 years in academics, R&D work, and contributed in various administrative responsibilities. Like, he has been warden and chief warden of hostels, chairperson of several committees, faculty coordinator of various academic, social, cultural activities. He has conducted many workshops, faculty development programs, and session chairs for IEEE conferences. He has developed startup named Shastra Automation LLP in 2017, under which He and his team developed auto-dimmer device for which he was awarded first national patent for ABV triple item Gwalior in 2018. He has been PI and co-PI of 9 major sponsored research projects by AICTE, DST Serb, CSIR, DRDO, DAD-RISE, Germany, and DEITY New Delhi. He has been awarded Bharat Jyoti Award by IFS New Delhi in 2011, Nanoscience Research Award, Gwalior Vikas Samiti Gwalior 2015, Abdul Kalam Gold Medal Award, Jaipura, Tamil Nadu 2016, and Shikshak Samman in 2019 by District Rotary Club Gwalior, and Atal Outstanding Teachers Award 2022 of ABV Triple Item Gwalior, along with other various national fellowships of UGC and DST New Delhi. He has supervised 10 PhDs and more than 104 master's theses published and published more than 223 research papers in international and national referred journals, conferences, and seminar proceedings. His research interests include condensed matter physics, computational nanoscience, nanoelectronics, energy storage materials, and quantum computing. He has written 2 books and contributed 4 chapters in various international books like CRC Press and Nova Science Publishers USA. He is member of many professional and academic bodies and delivered invited talks in abroad. Professor Srivastava has been the reviewer of many national and international journals, and he has foreign research collaborators from University of Florida, USA, Indiana University, USA, Trinity College, Dublin, University of Exeter, UK, and SDU, Denmark. I now request Professor Srivastava to kindly deliver his talk on quantum computing. Please, sir.
Thank you, madam. Thank you very much. And I am very honorable from Amity Gwalior that he has invited me for this talk. A very recent talk. So, good afternoon to everybody who are present here online, all participants. I think how many participants are here? Yes. So, this topic which I have chosen today to deliver to you, that is quantum computing, from all walks of life and from every corners of the world, everybody is now talking about quantum technology. So I think everybody know about this term nowadays, and it's become a very hot topic of research these days in scientific world. Before going to it, I just would like to use about this quantum computing techniques, quantum computing or quantum technology. What is the genesis of this quantum computing? What is quantum computer? How it works? How it is different from classical computing? So, what is a quantum computer?
Sir, you can go to slideshow mode actually, sir.
Sorry?
Thank you, sir. I was saying go to slideshow mode, please.
Yes.
Now it's fine, sir. Thank you.
So, first thing is that, what is a quantum computer? How it is different from a classical computer? Because the term which is prefixed here, quantum, and that is uses is going to have quantum mechanical phenomena to perform operations on data. On the other hand, that classical computer is based on binary bits, and that uses voltage flowing through circuits and gates, which can be calculated entirely by classical mechanics. So nowadays we are using our classical computers, which are based on bits. But when we talk about quantum computer, really it's very big, very new kind of technology, and everybody has focused on this because, in future or within 10 years, we will have quantum computer in our hand. So it's pertinent to understand what is a quantum computer in scientific world. So no doubt that this quantum computer has raised more and more increasing interest within the scientific computing, because of various reasons, you know. Why various reasons? Because it is highly interdisciplinary nature of the subject. Now the question arises, why it is interdisciplinary nature? Why it is highly disciplinary nature? Why? Because it includes computer science, physics, quantum physics, and other than that of the information technology. So it has revolutionary technological implications in the near future. And the point is that one can use quantum mechanics to process and transmit informations. So what is information? Basic question is, what is information? And everybody knows that information is something manipulation of different kind of data. But point is here, these quantum techniques, by making use of quantum techniques, one can implement fully secure cryptographic systems. So everybody is now going to transformation of classical computing to quantum computing. Now and again, there are one questions, classical mechanics and quantum mechanics. I think as a physics persons, if the participants are from physics background, they know very well about the classical mechanics and quantum mechanics. But the question arises, we are working towards the quantum mechanics if we have already classical mechanics. So the answer is very simple, that whenever we are moving towards the low dimensional kind of things, classical mechanics fail, and now we have to depend on the quantum mechanics. Because whatever the phenomena we have to deal in quantum mechanics, they are all related to low dimensions, low dimensional kind of things. Why? Because we have all devices. We are going to have day by day very, very low dimension of kind of things. So that's why we have to understand a very important mechanics, and that is called the quantum mechanics. Though it is very difficult, most people say that it's very difficult in nature, but once it becomes a practice, that is not a difficult one, because it's become the order of the day. Now, if you go through classical computing, you know, if you see the mechanics, inventor of different engine in 1834, and that is the full version here in 1815 to 1852. Ada Brand, Lady Lovelace, the full version of this machine was built in 1991 by the Science Museum. Thereafter, you can have cracked by Turing with the help of Colossus. It's a huge kind of programmer here, first programmer. And thereafter, you can have different kind of electronics like ENIAC, electronic numerical independent computer, was built in 1946. Just you can see, this is the thing, the that people are using this kind of computing there with a huge space, with a large number of different kind of things there. And this is the whole place, like built in University of Pennsylvania. 18,000 weighted 30 tons, required 6 operators, and it required 160 meters square of space. These are basically tubes which were previously used. Now we are using different kind of transistor chips, integrated chips. But previously we are using this kind of tubes there in order to compute, in order to different kind of calculations there. Now, if you see the journey of transistors in 50 years, you know, that is going to transform from 1 transistor to 10⁻⁷ transistors. And you know that first transistor was in 1947, that is developed by Bell Laboratories, Bardeen, Braden, and Shockley. Thereafter, it comes to a journey about this kind of transistors, CK703, packed kind of devices. And thereafter, in 1958, you have first integrated circuit, 1950, that is developed by Kilby and Texas Instruments. And in 1997, you have Pentium processor by Intel. So this is short journey. This is short journey of transistors, because everything is going to drive with the help of transistors. Everything, whatever devices, you can have use of transistors there. If you talk about the applications, now classical computers for many computational tasks, your bank account, your washing machine, your track control in the car, your science, your agenda, whatever. Everywhere. Classical computers now prevailing whole of the life, you can say. Now, this is the background, classical computation. If you go through it, like input here, you can have 2 plus 2. You can have computation or a simple kind of calculator. You will get output 4. So this is the way. If you simply program it hello.exe, you can have hello world. And then what is the essence of computation? This is the basic question which everybody mind has to pick up mind and click the mind. What is the essence of computers? Why it is required? Everywhere required now. Because we are dealing with big data. We are dealing with huge number of data. We have to calculate lot number of calculations, complicated calculations. So that's why we require nowadays different kind of servers, different kind of workstations. They perform our calculations in very less time. Now we talk about the classical computation theory. If you go back, the Turing thesis, Turing kind of principles there. So computation is anything that can be done by Turing machine. And this definition coincides with our intuitive ideas of computation, like addition, multiplication, banded logic, etc., whatever. So what is Turing machine? I think most of the people you know about this thing. This is something finite state automation. This is control model. And then you have previously you have some kind of read write heads there. And they are going to flow in this 10001 such in this kind of things there. Now input is here. If you're going to give some input here, you will have some kind of computation. And then you can have different kind of outputs there. So in the form of output, 1111010 whatever. Now, what kind of system can form universal computation? See, this is the journey. Life, different kind of life systems, real life problems, where you can use different kind of desktop computers, different kind of billiards ball you can understand. This is the best example of your Compton effect. This is something, this is some sort of cellular automata. These can all be shown to be equivalent to each other and to a Turing machine. The big question is what next? Because these all things we have to compute. Everywhere there is some kind of universal computation. Computation, the nature may be different. The nature of computation may be different. But you have to use bits, different kind of classical bits, binary bits, by making use of transistors. But the problem is going to have different in nowadays, because we have to deal different kind of complicated questions, different kind of complicated problems, and that take too much time. So that's why there is a need of this kind of computing, and that's why this quantum computing is the next generation of quantum devices. You can have here, why bother? Why bother this kind of competition? Because, everybody knows about Moore's law. So in this way, you can see this is the number of transistors which is going to have. Every 18 weeks, 18 months, your transistor number of transistors is going to be doubled. And two on different kind of dimensions, different kind of sizes. So one can hit the quantum level by 2023. You can have this kind, like here, this is the up to data of 2000 here. But you can imagine how the number of transistors is going to increase on very small size. Now the problem is that your heating effect to take place, and that is going to burn the device. Again, there is a very big problem. But due to advent of nanotechnology and due to advent of this quantum mechanics, due to advent of this kind of quantum computing, the things are become so much easier now. Let us see how this is going to happen here. So this kind of idea of a computational device based on quantum mechanics that was first explored in 1970s. The idea emerged when scientists were pondering the fundamental limits of computation, and technology continued to abide by Moore's law. So shrinking size of circuitry packed onto silicon chips eventually reach a point where individual elements would be no longer than a few atoms. So just you can imagine, shrinking size of your circuitry packed onto silicon chips. Now people think about how we can manipulate a single atom. This is a big question, billion-dollar questions. Because, you know, a bulk material can contain 10 power 24 atoms. But people nowadays are playing with few atoms. How is it possible? And with full capacity, with higher efficiency. That is possible because of this nanotechnology. And you know that at the atomic scale, the physical laws are quantum mechanical in nature, not classical. Not classical always. That is a great transformation from classical to quantum. So it's the beauty of quantum mechanics that it raises the question of whether a new kind of computer could be devised based on the principles of quantum physics. Though, you know, without classical physics, you can't have your quantum physics. The simple reason is that, or simple difference is that classical mechanics always deals with macro kind of things, whereas quantum physics or quantum is the low dimension kind of things. And this is possible because, you know, quantum mechanics always deals with low dimension. That's why every device, if you already observe that in day-to-day life, we are dealing with smaller than smallest kind of devices. And that's why quantum mechanics becomes possible in order to invent quantum computers. Because in quantum computers, quantum mechanics is going to handle there. So need for speed, you know, why we have to bother about the speed? Because if size of any problem is going to increase, like matrix order. Previously, we have a very small kind of matrix like 100 cross 100 matrix order of problems. But nowadays, we have to build 1000 cross 1000 kind of matrix. It's too possible with the help of this kind of things there. So, number of transistors on chip doubles every 18 months. Downscaling of circuit board components is leading to discrepancies. Copper traces actually crystallizes and sorting out. And thereafter, you have one operation at a time. 64-bit classical computer operating speed measured in gigaflops. But quantum computer, you know, harness atoms and molecules to perform memory processing tasks. So you have to focus on power of atoms. How single atom, how a few atoms can play a big role in case of quantum computers. Parallel processing takes place, millions of operations at a time. You know that 30-qubit quantum computer is also processing power of conventional computer that running at 10 teraflops, trillions of floating point operations per second. Just you can imagine. Also, you are going through this qubit. You know, this is a new term, qubit, that we will discuss later on here in this further slides. Because till now, we know about bits, 0 and 1. But in case of quantum computing, we can have your qubits. That we will discuss about. What are qubits here? So computational complexity is what? Why there is a need of what is computational complexity? Just understand a very small example. A very beautiful example here. An input x is quantified while information content, suppose L equal to log 2x. A calculation is characterized as of steps, logical gates, Okay. And the problem is like P level. If S is polynomial in L, so you can have S is up to L power mu. A problem is deemed to be hard if S is scale exponential in L. So a classic hard problem is that prime factorization. That is the most important part. For any kind of calculation, the most important part is prime factorization. It is applicable in classical computing, or you can say quantum computing, everywhere. The tough task is to have your factorization of numbers, factorization of prime factorization, you can say. Given a non-prime numbers, find its factors. The best known algorithm is this one here. Okay. A modern computer can factor 130 decimal digits. If L equal to 300, here, this is L here, right? In a few weeks, this is given here in this page. During doubling L would take millions of years to carry out these calculations. A quantum computer would do the job within minutes. This is a very important change from your classical computing to that computing. And people are still working, and research is going on, and it is proved theoretically, and also with some physical quantum computers by the IBM, and that a quantum computer would do the job within minutes. So that is the beauty, that is the change according to technology here. So this is something very important, public key. And in this way, you can see this is RSA. RSA is very important, PKE, public key encryption. Already people are using. Okay. So this is something encoding, this is something decoding. A quantum computer would crack this encryption scheme. This is the most important part here. This is the thing which is prevailing nowadays. RSA, RSA kind of encryption. That is called public key encryption. But a quantum computer can break this encryption scheme. This is the point. This is very important point. So critical quantum information science is driven by three great ideas: quantum computation, quantum cryptography, quantum error corrections. These are characterized with these different kind of subheadings. And quantum computation, you have three stalwarts here. Feynman, a very well-known picture, very well-known authority. Dios 85 and Sor 94. These scientists has played a very important role in the development of quantum computing. A computer operates on quantum states, can perform tasks that are beyond the capability of any conceivable classical computer. Now, finding prime factors, that's a very difficult task for any kind of computing, right? This is something here, you can equal, and this is something here. So what happens? This is going to have by Sor 94, he is finding prime factors on the basis of some quantum algorithms. And that works very well, already tested. In the area of quantum cryptography, these two persons have worked a lot, Bennett and Dressert. They have done a lot of work, and their quantum cryptography plays a very important role in today's technologies everywhere. Eavesdropping on quantum information can be detected. Quantum protocols can be unconditionally secure. So one can predict that quantum protocols, quantum cryptography are more secure than any classical cryptographies. That is already been proved. Like one of the important, like very important, good example. This is something Alice, this is something Bob. One is hackers here, have. Privacy is founded on principles of fundamental physics, not the assumption that else proper requires a difficult computation. Gathering information about the quantum state inevitably disturbs the state. It's very clear. Physics is so important because, physics is the mother of all natural languages. Physics is the mother of all science. But nowadays, people are not taking much importance to physics. You are also observing this thing. But without physics, nothing could be happened. This is clear from this kind of technology, today's technology. What the technologies are going to develop right now, you will find that everywhere physics is involved there. Without physics, it is not possible to develop any kind of technologies. That I am going to assure you. So, if you are talking about quantum technology, this is a very evident example. Everybody is talking quantum technology, but without quantum physics, quantum technology is not possible. Not possible. A lot of fund is going to be spent by the government of India. 6,000 crores of rupees has been sanctioned for quantum technology in India for research. A lot of work, a lot of zones, a lot of groups are going to be formed. Because really it is going to play a big role in the society, everywhere. So, you have two physical systems, like, what is the difference between here? Human and chip here, imperfect hardware, hierarchical architecture with error corrections at all scales. And this is something chip here, Intel Pentium 4. It is reliable hardware. Information processing prevents information loss. That's a very important point here. But again, I'm asking the same question. What is information? The subject of quantum computing breaks together ideas from classical information theory, computer science, and quantum physics. That I have already told you. Classical information theory, computer science, quantum physics. So this is going to be developed with the help of these three important areas. That's why it is interdisciplinary kind of thing. Information can be identified as the most general thing, which must propagate from cause to an effect. Anybody can ask, what is information? And very simple question can say that information is something, data, analytics, manipulation of data. And what is, in a simple word, you can say, information is nothing but is cause to an effect. Without cause, no cause effect is going to happen. Because for any kind of event, some information is going to happen there, is going to create there. So that's important role in the science of physics. And the full significance of this function is a basic concept in physics is only now being discovered, and this is especially true in quantum mechanics. So the theory of quantum information and computing puts the significance on a firm footing, and these are the use of quantum states to permit the secure transmission of classical information. And that domain is called the quantum cryptography. Secure transmission. So this is the area where people are working a lot, and that is called quantum cryptography. And that's very important in nowadays. How you are going to send your information in secure manner. But still, always you have a vision that this message or this thing hacked, something had this laptop had, this computer hacked, this server hacked. because we are using classical kind of cryptographic and this kind of theorems there. But now, due to advent of quantum cryptography, things are become much more secure. So this is one of the important area of research, quantum cryptography. The use of quantum entanglement to permit reliable transmission of quantum state, that is called teleportation. And you have something more kind of thing here. A quantum computer hosts quantum bits, which can store superpositions of. So one important point is that in case of classical bit, you have 0 or 1. Bits, 0 or 1 bits. So you can use either 0 or 1 at a time. And in quantum bit, the difference is that you can use 0 and 1 as well as superposition of both. And that is called the quantum bit. In classical bit, which we are using in classical computers, in our laptops, in our PCs, which we are using today, that works on the manipulation of 0 and 1. Everybody knows. In quantum computers, qubit or quantum bit is going to be used. So in case of quantum bit, you are using 0 and 1 as well as superposition of both. That is the basic difference between these two. Like qubits, you have particles spin. That's very important example here. Because, spintronics, one of the important area now coming, that is spintronics. Rightly, we have used our digital electronics. There you can use electrons as a driving force. But in spintronics, we are using spin as a driving tool there. Why? Because if you go below the electron, in a single electron, you can have spins, spin up and spin down. One electron is spin up and spin down. So in quantum computers also, these spins plays a very important role. The combination of two, spin up and spin down. Suppose both are spin up, you can take superposition of both like 1, 0, 0, or spin 1, spin down, you can cancel out, you will get 0. So this kind of manipulation is going to handle your quantum computers. Similarly, you can manipulate your atoms there. And you can also hear conventional computers, no matter how exotic, all obeys the laws of classical physics. On the other hand, quantum computer obeys the laws of quantum physics or quantum mechanics. The basic component of classical computer is a bit, a single binary variable of value 0 or 1. Here in this way, at any given time, the value of a bit is either 0 or 1. The state of the computer is described by some long bit string of 0 and 1 in this way. This is the way how a classical computer works. Okay. So here, basically, either it uses 1 or 0 or 0 and 1 at one time. But in case of qubit, it's a two-state system which obeys the laws of quantum mechanics. Again, I'm just already told about this one. This is something spin 1 and this is something spin down. 1, ket 0. These are the notations of quantum mechanics. I think most of the people know about the quantum mechanics. And what are different notations about it? So these are valid qubit states or quantum states. Like psi is here. This is something wave function psi. And this is most important notation of quantum mechanics, wave function psi. I think everybody knows about this thing. And this you can have here 0 and 1. or you can have combination of both, right? In this way. So the state of qubit can be thought of as a vector in a two-dimensional Hilbert space spanned by basis vector ket0 and ket1. So basically, this wave function psi, which is the major part of wave function psi, and you know that what is the physical significance of wave function psi? Can anybody answer it? What is the significance of wave function psi? Is there any permission to participants to interact? Yes, ma'am. Yes, Dr. Pankaj.
Yes, sir. I'm just coordinating. Just give
Yeah,
me
yeah.
some time. Just coordinate.
Because everybody is mute here.
Actually, that is muted by IT host. I'm just coordinating, sir. You just give me 2 minutes.
Okay, okay. Okay, anybody? I should continue now. So, basis vectors in case of qubit is ket0 and ket1. Now, my question is, what is the significance of wave function psi? You know, psi is the probability of identifying any particle in space. Okay. So, how does the use of qubit effect computation here? This is something valid states like one.
Sir, you can interact now. All rights are given. All can interact now.
Okay, fine, fine. Thank you. So, question is, how does the use of qubit effect computation? This is the way how you can have. This is a classical computation here. Here is bit 0 and 1, valid state 0 and 1 at a time. 0 or 1. But what about quantum computation? This is something you can have spin up and spin down, ket0, ket1, ket1 and ket0. And valid states are here. C1 ket0 plus C2 ket1. Means superposition of these states. You can use either 1 ket1 or ket0 or superposition of the states at the same time. Right? So which one is more highly computed in less time? Because of superposition. You can have ample options to calculate the things like ket0, ket1 and superposition of both things here. So this is the basic. Here you can use either 0 or 1 at a time for any kind of computing. But here you can use here superposition of both also at the same time. So that's why your speed becomes much higher. How does the use of qubit effect, that is classical computation? If you go through logical valid operations here, okay, 0, 1, 1, 0, whatever, and then you can have valid operations in the same pattern here, quantum computation, unitary valid operations, like 1 qubit. Here is matrix plays very important. Matrix, polymatrices, you know. Yes, anybody? You know about polymatrices, I think.
Yes, sir.
अब तो क्या गेट की कोशिश है चल भी जा रही है.
X, Y, Z, I. 4 poly gates are there.
Yeah, that's true.
This is Hadamard gate.
Yeah, that's true. That's true. So these are basically unit valid operations. So these matrices, polymatrices, act as the operators in case of quantum computers. What is here? In case of classical computation, you have 0, 1 only. Okay? 1 bit, here is 2 bit kind of things here. Okay. But here, these sigma x, sigma y, sigma z, and HD, Hadamard matrix, these matrices play very important role for quantum computing because these are basic ingredients of quantum computing. Okay. So you can have this C0 here, 2 qubit kind of states here. So they can act as the operators on different kind of wave functions. Okay. So measurement, how you can have measurement in classical computation here, deterministic in nature. Okay. State 0, result of measurement 0, x1, this is measurement is 1. So this is highly deterministic in nature, but quantum computation is stochastic. Like cat 0, 0, cat 1, 1, but here, just see superposition of both. You have 50% chance here, 50% 0, 50% 1. So this is something undeterministic.
Measurement collapses the superposition.
Yeah, maybe. But nowadays, people are working because there are two limitations in case of quantum computing. One is decoherence and another is error corrections. Entanglement, entanglement takes place here. Okay, because of superposition, the states become entangled. That's an obvious process. That's an obvious event. But due to kind of different operations there, people have overcome this kind of limitations. Okay. So they're making use of different, Hilbert space qubit, 2 qubit states here. You can see here. And arbitrary state. There is something operators. They are going to operate on this side. This is something unitary operator. U1, U12, U21, U22. And it is going to operate on this side wave function C1, C2. Okay. So this is single qubit kind of problem. If you go for simple different kind of complex problems, you can have more and more qubits are going to increase, like 2 qubit, 3 qubit, 4 qubit, and so on. So they are using this kind of operations, like metric operations. So matrices plays a very important role in quantum computing. That's the point here. Okay. Now circuit model, if you go through circuit models, this is 1 qubit operation, sigma x. 2 qubit operation, C naught is there. And measurement, you can have different kind of measurements there. Okay. This kind of step by step operations is going to take place. In case of classical computer, you have classical circuits in the form of wires and so on. But here, in case of quantum circuit, you are just using different kind of matrix operations. That's all. Okay. Okay. So now just see, separable state can be written as tensor product. This is something tensor product here. There are two kind of data here. Sorry. So this is something wave function psi here. And this is something tensor product of two wave functions, like one is phi and another is chi. Now due to this kind of thing, tensor product, you have entangled states cannot be written as a tensor product. That cannot be written. Okay. So that's why if you take it into account both of the difference between the two, you can have classical bit as well as quantum bit or superposition of those. So this superposition of both states not continuous in nature but discrete in nature. And what is quantum entanglement? Two or more objects must be described in reference to one another. Entanglement is a non-local property that allows a set of qubits to express superpositions of different binary strings. So, due to superposition of states, entanglement takes place. That is the obvious operation is going to handle there, is going to take place there. Because naturally, when you are going to superimpose two things, like if you take young double slit experiment, please recall your young double slit experiment. Two sources of light are going to superimpose each other, and thereafter you will get dark and bright fringes there. Okay. So in this way, you can have this kind of things here. And if you classical versus quantum bit here, you can see can be measured completely. Classical bits can be measured partially, that we have already seen here. They are not changed by measurement, and they can be changed by measurement. Here it can be copied, but it cannot be copied. This is one of the important feature of quantum computing that cannot be copied. Can be erased. This classical bit can be erased, and this cannot be erased. So once whatever the coding or whatever the quantum algorithms you can made, whatever the coding you can made, you can't be erased. And that's why it's highly secure in nature. It is not going to be hacked by anybody. So this is the beauty of quantum bits versus classical bits. This is the unit of quantum information qubit. Golden rules that plays here, quantum mechanics. That are waves that can be state superposition, alpha ket 0 plus beta ket 1. And in this form, they are going to take place here. As long as you don't look, just you can see quantum measurement. Like flicking a coin, you will always have a probability of head or tail. Similarly, you can have here also. And that's why partial kind of probability here, 50-50%. Okay. So bit is basic unit of computer informations, regardless its physical relation. A bit is always understood to be either 0 or 1. And in analogy to this, a light switch and 1 off and on position. A qubit has some similarities to a classical bit. Like bit, a qubit can have two possible values, normally 0 or 1. The difference is that whereas the bit must be either 0 or 1, a qubit can be 0, 1, or superposition of both. That you must understand. This is the basic concept of quantum computing. So this is a linear superposition here. A pure qubit state is a linear superposition of those two states. This means that qubit can be represented a linear combination of ket 0 and ket 1. Okay. So that's why it is written here, ket psi is equal to alpha ket 0 plus beta ket 1. Now, what is alpha and beta here? They are the probability amplitudes, and can in general both be complex numbers. So when we measure this qubit in the standard basis, the probability of outcome is mod alpha square and mod beta square. Because probability amplitude, that can be calculated in this way. Simply because this ensures you must measure either one state or the other. That is the way how you are going to calculate your probability amplitudes. And what is the probability of maximum probability of any event to occur? Anybody? I am asking this from the participants. Can anybody tell me what is the maximum probability of any event to occur? Yes, anybody? So maximum probability of any event to occur is 1. Yes.
Sir, they are writing answers on chat box, sir.
Okay. Actually, this is the whole screen I have taken into account here. No problem.
One they have written, many of them.
Yeah, that's good. I am not able to see this thing because this is the whole screen figure here.
Yeah.
So, quantum computing and quantum information is going to include quantum mechanics, computer science, digital design, information theory, and cryptography. This whole thing is going to comprise about quantum computing. Now the question is, you must have some kind of physical quantum computer. Otherwise, how it will work? How it will work? So quantum computing is a hypothetical device for computation that makes direct use of quantum mechanical phenomena such as superposition and entanglement to perform operations on data. Whereas in classical computer, information is stored as bits, and this is in case of physical quantum computation. So the basis is a classical computer is a memory made up of bits. A quantum computer maintains a sequence of qubits. That is one of the important parts. Okay, this time because I've already told you. Yes, one thing important here. In a quantum computer with n qubits can be up to 2 power n different states simultaneously. This compares to a normal computer that can only be in one of the 2 power n states at any one time. This is 2 power n different states simultaneously. Whereas in comparison to those of normal computers, you can have one of the 2 power n states at any one time. This is one of the important difference. Okay. So these qubits are going to operate by quantum logic gates. In case of normal computers, classical computers, you have classical logic gates. Here we have quantum logic gates. Okay. Now the implementation of qubits for quantum computer could start with the use of particles with 2 spin states, up and down, which I've already discussed about this thing here. Okay. And this we can have different kind of conjugates because for any kind of physical quantum computer you need some different kind of conjugates like materials because material is required in order to have your physical kind of computer. So here people are working superconductor. They are using superconductors, trapped ion quantum computer, nuclear magnetic resonance, quantum dot, fluorines, SR based quantum computers. So there are different kind of requirements like qubit implementation itself, control of unitary evolution, initial state preparation like qubits, how you are going to prepare your qubits, and thereafter finally measurement of final states. This is something input, this is something output. For any kind of computer you can have. Input states as well as output states. The same procedure is also going to happen here. Requirements like implementation requirements here, qubit implementation, control of unitary transmission, and thereafter measurement is the best last one. And you are going to implement on different kind of quantum computers like NMR kind of computer, optical photon computer, solid state quantum computer. A lot of research is going on by choosing different kind of physical realization of quantum computers. Okay. So this is optical photon, that is going to use different kind of photons and resonator, either beam splitter, whatever. NMR that uses spin of atomic nucleus to represent a qubit. How these things are going to work because nuclear magnetic resonance. Here they are using spin of an atomic nucleus, spin up and spin down to represent a qubit. In previous slides, I have already told you about this thing. Spin 1 and spin down. Spin 1, suppose it is 0, spin down it is 1 or vice versa. So in this way, they are going to represent NMR kind of quantum computers. Okay. Spins are prepared by magnetizing and induced voltage are used for measurement. NMR will not scale to more than about 20 qubits like that. Yes. Now the next stage is of languages. What kind of languages they are using? What kind of languages can be used or people are using? Even though no quantum computer has been built, that hasn't stopped the proliferation of papers on various aspects of them. But you can have here QCL, QCL, C-like syntax, C language, and very complete. QGCL, it is also in quantum C. Currently, just a specification here, quantum C language, and they are using such kind of languages here. Now, if we talk about quantum gates or quantum circuits, and you know that classical computer is built from an electrical containing wires and logic gates, and the wires are used to carry informations around the circuit, and these logic gates perform manipulations of the informations. But a quantum computer is built from quantum gate circuits, quantum circuits, containing wires and elementary quantum gates to carry around and manipulate the quantum informations. So this is the basic difference between your classical gate, classical circuits, as well as quantum gates and quantum circuits. Like single qubit gates, classical single gate bit logic gates, NOT and NOT gate, whose operations is defined by truth table 0110. Okay, and that can be changed. Can an analogous quantum NOT gate for qubits be defined? In fact, the quantum NOT gate acts linearly. It takes the state alpha ket 0 plus beta 1. Okay. In this way, you have different kind of quantum gates. Hadamard gate, whose matrix orders are in this way, 1 upon root 2, 1, 1, 1 minus 1. Poly X, 0, 1, 1, 0. Poly Y, 0 minus I 0. Poly Z, 1, 0, 0 minus 1. So, quantum gates, basic quantum gates, they are being used as a gates, as a quantum gates to manipulate or to make different kinds of quantum circuits. And thereafter, they make some different kind of combinations and they work as a quantum computing. Like for example, just see here, one input gate, not here. Input gate is ket 0 plus C1, 1. Output state is something reverse of this. Just see here. Here is C0, here is C1, here is C1, here is C0. So that will act as something not inverter. Okay. Pure states are mapped as 0 to ket 0 to ket 1 and ket 1 to ket 0. Gate operator is something here like matrix 0, 1, 1, 0. and you are going to operate on 0 ket, you will get 1 0. Similarly, if you are going to have ket 1 here, you will get the reverse one as expected. 0 1 1 0 0 1 1 0, you will get 1 0 0 1. Okay, so in this way, this is something 0 1 1 0, you will get 1 0 0 1. That will act as a NOT operator. That will act as an invert. Are you getting this point? So this is the way how the mechanism takes place in quantum computing. This is a 2-input gate, like control NOT and C naught here. This is a representation of C naught, and this is something here, C naught matrix. Okay, and they are going to operate one by one here. C naught maps this one, you will get this one. This is valid only for pure states. So this way, the things are going to happen. 2-input gate, 3-input gate, and so on. 3-input gates like here. Controlled C naught, C square naught, or Toffoli gating को बोलते हैं. This is called Toffoli gate. It is going to operate on different operations. And this is something quantum circuit. This is representation of quantum circuits. So
could you
this way,
explain how
the
does it
thing-
work?
sorry,
3-input gate.
sorry, yes,
Please
please.
explain how does it work? Toffoli gate.
Yeah,
How
this
does
is
it
called Toffoli gate, and this is the matrix representation of Toffoli gate. Right? These things are going to operate on different gates. Okay, in a sequential manner.
be?
Like this is the something you can see here. This is something diagonal kind of matrix here. Okay, and this is something here. It is going to operate C square naught.
No,
That's
if
why
I
it is
supply
called.
a 3-bit input, how
Yeah.
will I get the output? Maybe. What
That
is
is-
the output maybe if that's for a 3-bit input?
Through 3-bit quantum input, you will get one by one. This one, and this is something AB, and this is some addition operation on the C part of thing here. Okay, this is just a representation. You can just see here. Okay, this is general control gate. In a sequence manner, you can use this one and this one. Thereafter, this will going to operate U. Then it is going to operate on CU. Then it is going to operate on C square U one by one, and then etc. You can use, and then you can further you can get the output. So this is a circuit is a sequence of quantum gates that is linked by wires, and that's why the circuit has fixed weights corresponding to the number of qubits being processed. So this is basically a process. This is the mechanism. In a physical quantum computer, you can have such kind of mechanism that is going to operate in some kind of physical realization. And these things are going to have written different quantum algorithms in different quantum languages. And they are going to operate on different quantum physical computers. Process is same as that of the like classical computers. The point of difference is only that it has some kind of superposition of 0 and 1 and whatsoever. Okay. In case of quantum communication, you can have here like quantum channel, quantum cryptography, quantum telegraphy, teleportations. There are different applications in case of quantum communications. Like here, you talk about quantum channel, a communication channel which can transmit information as well as classical information in the form of different documents. These are different areas like quantum cryptography, quantum key distributions, that is, use quantum mechanics to guarantee secure communication. So it enables two parties to produce shared in random bit string only to them, which can be used as a key to encrypt and decrypt messages. Okay. This is the way how the things are going to have some kind of things here. Very simple example. People are experiments performed by the Bennett and different scientists there in 1988 to 1998 here. Okay, just in the quantum teleportation with photons, in different kind of pulse nature, quantum channels. This is something river Danube you can see here. This is a classical channel, normal channel, and this is the quantum channel. This is just an example. How the transformations takes place from one place to another place in the form of quantum bits. This is the way. They have referred in this paper here, but it is old paper. At the first time they have used this kind of knowledge, and they are used there in theoretical way. Like communications, like one is Alice and Bob trying to communicate their messages. Here is hacker here. Eve is not happy about this. He wants to listen and interfere here. So what happens? Basic scheme based on polarization scheme. What is the basic scheme? Suppose you are using some photons, light photons, in order to transform your information, quantum informations. So photons are transverse magnetic waves, as we know. Magnetic and electric fields are perpendicular to the direction of propagation, and they are perpendicular to each other also in this way. So we will assume that we are dealing with linearly polarized light, but other schemes are possible. We need to create photons that with an electric field oscillations in the desired magnetic plane. Okay. So one way to use this by passing light through an appropriate polarizer. Only vertically polarized photons are going to emerge from this. Okay. So in this way, it is possible to detect absorption by using calcite crystal. This is something light, and this is something photon detector. This is something one polarized and another polarized, unpolarized light here. These are different kind of things. So through calcite, you can have orientation of polarized light. They get detected in different photon detectors. So that polarization of photons can be arranged. Vertical polarization denotes 0, horizontal polarization denotes 1. It is up to you that how you are going to code this thing. Okay. And then you can have like Alice sends 0 in this scheme, and that Bob uses a photon detector with the same basis. So Alice sends 0 here, and Bob receives in the same fashion 0. Suppose Alice sends 1 in this way, in this direction, it should have to receive in this way. So this is the way how the rectilinear basis. This is the rectilinear basis, and you can also change it by giving some different directions.
So what exactly is basis here? Could you please explain?
Basis is that you can use, like you want to send in this direction, X, Y, Z. Okay. So it is up to you that you are going to send your different informations in vertical directions, like 90 degree. Okay. Or you can use different kind of angles.
So either align or either orthogonal.
Yeah. In any kind of angle you can given. So point is that if you send like 45-degree angle, any information, so that must be uncoded or decoded by the end user with that kind of 45 kind of things. Otherwise, it could not be detected. Okay. So this is the way how the information is going to transform with the help of photons. So this is some kind of diagonal basis or different kind of angles there. Different bases also you can have here. Sender can encode 0 or 1 by choosing the polarization of the photon with respect to basis, like vertical 0, horizontal 1, or 45-degree 0, 135-degree 1. So in this way, it is going to receiver bob and measure the polarization with respect to either basis. And if the same basis, then bits are correctly received. If different basis, then only 50% of bits are correctly received. This notion and one of the basic quantum cryptography key distribution schemes. This is the key to success of different quantum cryptography key distribution schemes. And a lot of research is going on this quantum key distribution keys there. Quantum cryptography.
So what about the 50% of the basis?
Yeah, it is not going to detect there. Like if you understand like Young's double experiment of quantum mechanics. If you see, after supervision, you will get dark and bright fringes there. Either 0 or 1, 1, 0, 0, 1, whatever. So suppose if it is in same phase, you are going to detect it or you are going to accept it. If it is 0, it is in opposite phase, you are not going to accept it. So this is the way of computing. This is the way of detecting or measurement of different quantum bits. And during quantum key distributions, it is from coding point of view that you are accepting or considering or assuming whether same phase or different phase, either 1 or 0. Okay.
Sir, when they are going to communicate, I think they're going to decide the basis. Okay.
Yeah. This is the basis. Is it decided by the coding?
How they will communicate the basis to each other?
Suppose you are coding in some different, like 45-degree, okay, in different basis states, okay, and the end point is doesn't know while measuring if he got that point on 45-degree, like 1 or 0, whatever. So point during measurement, if he got 1, it means he is detecting the right information.
No, sir. I just want to know, for example, you and me are communicating, and let's say I am going to transfer, I'm going to use the basis of 45-degree.
Yes.
Fine. So how do I will tell you that you have to use basis 45-degree so that you can receive the same bits which I have sent to you?
That is true. That is a true question. See, at 45-degree, he has coded some. Okay. Suppose he has coded like 145-degree. And the end point doesn't know that it is on 45-degree and we are going to detect or measure on 45-degree. So what he will do, he will try to measure on different angles.
Okay.
Where he will get 1, that would be his correct information.
He will always get a 1.
No. It is up to you whether you code your 0 or 1, whatever. It is up to you.
When I'm sending 101, let's say a bit 101.
Yeah.
Maybe how he will come to know that 101 I have sent, because if I'm sending a 1, you'll be getting 0.
So he will not going to accept, na? When he will get 0
only at 1 is going to accept.
When he is going to accept?
No, only when he gets 1 is going to accept.
Yeah.
Then how do you come to know what bits have been sent by the sender?
No, that is the point here, because for any kind of classical, suppose you want to send secure information, right? Okay.
Yes.
If you want to through in classical way, what do you want? What do you do?
Let's say 101 I want to send.
1, yeah, 1 or 0,
101.
Okay? So during 1, you will have same phase. Suppose.
Okay.
And when you will get 0, you will have
Different phase,
different phase.
90-degree phase.
Yeah. So if you are suppose you have made some kind of coding there from the one point of end, and you know from the and he has communicated you by any means that when you will get or when you will receive 1, then it would be
That's the thing I want to know, because I do teach cryptography to my students. Let's say when you or me are communicating, okay, and let's say we decide on one single key, how the key is going to be communicated, because there is chances of if teaching at any point of time.
That is true. So he
Yes.
he doesn't know that it is sent on 45-degree or any kind of angles. Are you getting this point? In classical communications, there is no some sort of different kind of angles or some different kind of or different kind of polymatrices there.
Okay.
That
sir,
is the
Fine, fine,
manipulation of 0 and 1 only, right? But here you can have superposition of different things there, and that too output is given by in different forms. At the end point, whatever you will get, if you got suppose 1 at different angles, or suppose that is sent by 45-degree. Okay, so at only 45-degree, the end point will measure the things. In between that, if any eavesdropper is in between them, he will not able to detect whether it is sent on which angle. Okay, so that is the point of security which is given through quantum kind of matrices there, matrix or quantum states. So during quantum algorithms, these physical algorithms could be made in order to in different languages, I mean, and that is going to be handled there in this way. A lot of papers are there. You can go through it because I'm not going into detail for that, because this is the elementary basic concept about all those things. Okay. So this notion underpins one of the basic quantum cryptography key distribution schemes, and that is the basis of quantum key distributions. So there are different obstacles and research. Like the field of quantum information processing has made numerous promising advancements since its conceptions, and it includes building of 2 and 3 qubit quantum computers capable of some arithmetic and data sorting here. But still, few limitations prevent us from building quantum computer that can reveal today. But nowadays, IBM and MIT have developed some short-range physical quantum computers, and they have tested up to some distance, and they are working very well. So it is anticipated that in future, they are still testing for more different large distance kind of communications. Okay. So a lot of scope is there, like quantum computing are still in fancy stage. And the future outlook is that you have this, because it's at pioneering stage, obstacles are being surmounted that will provide the knowledge needed to first quantum computers, and still a lot of development has been made till now. Quantum computers will emerge as a superior computational device, no doubt, and that's become the important point. Futuristic applications in quantum communication, in quantum bit commitment, true randomness, because they are going to generate quantum true randomness, veracity to programs that need true randomness in their processing, and different kind of code making, randomized algorithms for problem solving. These are different algorithms which have been developed. Those algorithms, Grover's algorithm, source factorization, and Simon's algorithms. These are different quantum algorithms. You can see different platforms, different websites. You can search there and then you can have very important, very interesting kind of algorithms. Physical implementations that I have already told you, that is quantum optics, atoms, photons, spin-based materials, quantum dots are being used in order to have your physical quantum computers. Okay. So you can have this kind of thing here. And for more further, if you want to interact, you can interact with personally in our institute, or you can personally contact me. Okay. So this is the end of this presentation here. Thank you very much. Any questions related to it?
Participants, if you have any question, you can write on the chat box, please. Sir, we'll wait for 2 minutes for.
Yeah, sure.
So there is, for now, there is one question which has come. How the data of quantum computation is more strong as
How the data of quantum
strongly secured than classical?
Yes. Because I have so many few slides there. Secured in the sense, because just I have discussed here, because from one point of view, don't know that how the coding you are doing to at one end, and that is going to be delivered by the another end. Because you have freedom to code in different angles, different kind of physical realizations, different kind of implementation schemes there, where you can have use the superposition technique of quantum mechanics. So when you use the quantum mechanics like matrices of different orders, that too is highly secure because it cannot be copied, it cannot be terminated anywhere in between that, between one end to the another end. So you can have a lot of literature, you can have a lot of papers, research papers. You can go through it on websites. That will help you to understand all those things in detail. Okay.
Anyone has any question can ask.
No, you can't be used MATLAB for quantum computation. Okay. Because there are so many open source simulators are available, like Qiskit, one of them from IBM. It is freely open software for quantum computing. Just you here, Qiskit, Qiskit, that I have not mentioned somewhere.
Sir, can you repeat? I'll write on the chat box.
Yeah. Yes. Just I'm typing here. Qiskit software from IBM. It is freely available through some of the like account you have to open, freely accountable, and you can use it. It's very good, very best kind of software for beginners. Okay, you can use it. You can make some quantum circuits. You can use different kind of quantum algorithms there in C languages, and then you can proceed it. That's very good for beginners. You can start from this Qiskit software.
I think so, sir. Anybody else has any question? Otherwise, we are going to sum up. Well, I think
Yes.
so. That's all, sir. I think that's all, sir. No more questions are there.
No, anybody can reach us on my email ID if they want to have some more informations.
Sure,
Okay.
sure, sir.
You can have
So-
you on like I have already shared my first pankaj@triple-item.ac. I'm just giving my email ID. Okay. You can reach me out here. Okay, for any kind of help.
So I would like to thank our speaker for today, Dr. Pankaj Srivastav, for enlightening us on topic of quantum computing. I hope the knowledge shared by sir is going to help the participants in their future endeavors. And for any query, as sir has said, you can contact him on his mail ID, or you can send us your queries and we can forward it to him. Thank
Sure.
you very much, sir, for sparing your valuable time with us and being with us. Thank you
Thank you.
for
Thank you very much to the Honorable Professor Pankaj Mishra, Professor Manisha, Professor Rinku Bhatia, and others of the MIT family, MIT University family of Gwalior. Thanks a lot to all of you and all participants. For any kind of query, any kind of questions in your mind, you are free to ask on my email ID, whatever. Okay, thank you very much.
Thank you very much, sir. Thank you. Thank
Thank
you.
you.
Thank you, everyone, and have a good day. Tomorrow we are going to again start at sharp 10:15. Thank
Thank
you.
you.
IT
Thank you,
host, you can
teachers.
close.